So when we talk about natural language processing in the computer science, when the whole idea was to learn the computer language to build software. So we try to learn the language of computers. NLP is, you can think of a reverse task. We are making computers to learn human languages. So that's where NLP comes into the picture. And there are two broad areas: natural language generation and natural language understanding. And so in classical NLP, you have various approaches to understand the natural languages, how natural languages structured, and how the semantics of those sentences are captured. And there is a generation task. We somehow with some approaches we make computer to generate human-like languages. It could be any languages, which is a natural languages. And initially, it was all based on language models we are using and various classical NLP techniques we were using. Now, with the development of large language models, all the natural language processing tasks like classification, summarization, and all those tasks can be done easily by large language models. However, initially there were classical techniques for doing this. So, just to give you a brief idea, all the language models that are there primarily can be categorized into three categories. So earlier they have started as an statistical based language models. From the corpus, you calculate the probabilities and then using the frequency of the word occurrence, and then you try to come up with language models. Examples like n-gram models, you can go and see. And I also show you in the previous session that probability of a occurrence of a sentence is basically composite using the probability of the tokens, words, joint probability of the words, product of the words. So then there is a improvement over it. We because text corpus increases and the calculation of the probabilities complex joint joint probabilities is easier to manage using neural network based architectures. So then neural network based architectures came into the picture. Same thing, it was going to calculate the probability of a sentence, which for example, okay, so I'll have example in this, so I'll show you. Can be managed using neural network architectures. Then there are some of the architectures like RNN and the variants of RNN like LSTM, GRU, bidirectional LSTM, bidirectional GRU. All those came into the picture. Then there were some problems in these architectures, and then we moved towards the transformer-based architecture. And when self-attention was proposed in 2017, unlike image models or computer vision models where you always use pre-trained models. So you can download ResNet or you can use YOLO or any other computer vision, for any other computer vision task, you can use any pre-trained model. Before 2017, it was not possible in case of NLP. So NLP area was not so popular compared to the computer vision task or image processing task. Because in image, you can always use a pre-trained model earlier as well, like CNN-based model or any other model. However, in NLP, when self-attention have been introduced in 2017, it made possible to pre-train, so to train large language models or language models over a big corpus of the data, and that enables the pre-trained NLP language models. So after that, the transformer came into the picture, where there are a lot of architecture. You might have heard about BERT, you might have heard about universal sentence encoder, Roberta. All those language models in this T5, GPT, all those models are based on transformer, and they are variants of transformer, and they are pre-trained over large corpus of data, and it was made possibly due to the attention-based mechanism. So after that, since now now we have a pre-trained model in case of languages as well, NLP tasks as well. Now the NLP area have boomed in terms of text generation and all. Now you can see the popularity of GPT, Grok, DeepSeek and all. So it was all level after 2017. So these are three types of language modeling. There are three types of mathematical tasks. So without mathematics, let me just give you a brief idea about it. So there are three type of tasks they use to train the model. So one is the next word prediction. So given a previous words, you try to predict next word. So some of the language models are trained based on this idea to learn the context of whole corpus. One of the idea to train the language models is masked word prediction. So given a text, given a corpus of data, some words are masked and model tries to predict the masked word. And then the loss and the backpropagation using that it try to identify or predict the masked word. And that's how the model tried to learn the context of the whole data. One is replace word detection. So another technique used to where words are replaced and model tries to predict which word is replaced. And by doing so, the model tries to learn the context of the whole data. Most popular one is the next word prediction, where given a sequence of the words, the model tries to predict the next word and so on. So it continually generates the data. So I hope it is clear till this point of time. Okay. So three types of models, starting from statistical to a neural network based, and we have transformer. And after transformer, there are LLMs. And after LLMs, there are compound AI systems, RAG based, retrieval augmented generation. And then nowadays we are hearing about agentic AI. So this is the basically sequence of history of the language model till agentic AI, which is currently you are seeing. So how mathematical model works? So you can, for example, for a word I saw a cat on a mat. So probability of the whole sentence is computed as like probability of I multiplied with the probability of saw given I multiplied with the probability of A given I saw and so on. So probability of I saw a cat on will be like this. So formally it is a product of conditional probabilities, also known as chain rule. In short form, it is written. So we have defined the function. So now we know how we can predict the next word given the previous words. Now the problem is how we are going to compute it. So one way is the n-gram based, we are not going to detail, which is the classical NLP based approach. One way is the neural network based. So we are going to see how sequence models capture this sequence of the words in the data. So once, let's say there are two ways and we have come up with a language model. So, okay. So you can see here, so given a sentence, let's say how text was generated. So I was, let's say, was there, and what words will be there here? Given a vocabulary, let's say you have a set of vocabulary from your data set. For each word, it generates the probability, calculates the probability, and the highest word probability is taken as a probability word taken as a next word predicted. So here, all those, so star means you're calculating probability for all the words that are there in your vocabulary in text. And from the top word, you are picking it as an expert.
Sometimes it is taking not the.
So it is an illustration purpose. So sometimes either we left it to the language model, how it is selecting based on probability, or it could be guided from the human as well. So top words from, let's say, top keywords are outputted, and it can select. Okay, so it's called teacher forcing training. So it was for the illustration purpose only, that how it is calculating. And okay, so the whole pipeline of neural network based architecture is something like this. You have neural network based architecture given some sentences, words as a tokens, and obviously these are the word vectors, because we cannot directly feed the word as a data to the model. We need to convert it as a numerical representation. So we need some vectors representation of words. So we use those vector representation, give to neural network architecture. Towards the end, it gives you context vector. It is a high level. I'll explain you in detail. That context vector, you can think of capturing the context of the previous words somehow, maintaining that sequence, and that vector is passed through some neural network based architecture to give the probabilities around all the tokens that you have in the vocabulary, and from those we can pick the highest one. So in simplest form, you use a neural network architecture. You give the previous sequence of words. It gives you the context of it. Again, a numerical representation, which you can give to the some dense neural network towards the end, applying activation function. So that gives you probabilities over the all the vocabulary words that are there, and then you can pick which one is the highest one. High level pipeline. If you don't understand, that's fine. I'll show you example of it. That I have already covered. So you cannot directly fed the words into the neural network architecture. So we need somehow a representation of words in form of numbers. And you can think of that word representation as a vector. And for example, let's say good word is there. So the whole idea of word embedding is to convert this into some vector consisting of some numbers, and those number basically representing that word in the word space. So you can think of a word space which is, let's say this is the dimension of vector is n, so it is n dimensional word space. So that vector, let's say for simplicity, it is only of two dimension, x and y. So in x and y, good is represented by one coordinate or the value of x and y. So this you can think of a word space, and once you have come up with a numerical representation, the whole idea of word embedding is that the similar words are are closer to each other. For example, good and better should be considered as the same. Good or bad should be considered as a opposite. So in the word space, you can think of this good and better are closer to each other, and bad is somewhere. So once you have a numerical representation, you can actually perform the arithmetic operation and the reasoning about it. So for example, let's say a word king is there, a popular example is there, and you have a representation of as a numerical representation king, and there is a representation of words of man, and so if you subtract king minus man and you add queen vector, you will get a vector which possibly representing women. So the word that you are getting, the vector somehow will be close to the vector which represent the woman. So coming up with the word vectors, you can actually perform those reasoning and keeping the contextual information of the words intact. And loss function, we are going to use the based on the task, we are going to use either cross entropy loss or any other loss function that we are using. So coming up to, so I'll skip this and I'll show you towards the end how training is done. So in neural network based architecture, we started with RNN networks. So you might have covered uh, a basic neural network architecture in this course. Dense neural network, how you give the input, pass it to the hidden layer, from hidden layer to output layer, and then you use back propagation to train it. For any, for example, if you have only two words, king and man, of let's say a word dimension of word vectoring of 8, so given to the neural network, there will be how many inputs? 8 into 8 inputs you will give together. In, let's say, even you are taking one word at a time, you will give 8 inputs at a time. And let's say you are giving a sentence, because in sequence modeling we are going to give the input as a sentence. So for example, I said, for example, I like this course, and all are representing by 8 word vectors. So these many inputs will be given as a together as a data to the neural network. But the problem is, basic neural network or even the convolution neural network cannot capture the sequence of the data. So ordering of the data, whether if I like this course, if I change it to like I this course and give this 8 vector first and then the other, then your neural network cannot identify that ordering. So ordering awareness is not there. Which word is coming after, which word is coming before. So sentence sequence does not matter in the neural network. So that's where this is the limitation of neural network. Why we need some models which can capture that ordering of the words as well. So that's where sequence to sequence models came into the picture, where you have RNN, recurrent neural network. So when we talk about sequence modeling, where your input is a form of sequence, your output may be a form of sequence, or it could be a number, or it could be simply a class. Not talking about the generative AI, I'm just talking about the sequence models. So some of the example like speech recognition. So you have a audio which is again a wave sequence, and your output will be a text sequence. This is an example of sequence modeling. One is the music generation. So input could be nothing or random number, or let's say I want to generate a music in the, for example, some integer may be representing the category of the type of music, So that could be a single integer, and output will be a wave sequence. Another column is sentiment classification, which is, given a text, you want to identify whether that text is a negative, positive, or neutral. So then this is given as an X as a text sequence, and the output is only single integer representing the sentiment. So you have number of tasks, and each task of a different type. Like this is of the sequence to sequence, it is one to sequence. This one is the sequence to one. And because in sequence modeling we have different tasks, we have variety of RNN models. Depending on the task, the type of model is different. And there's some other example: sequence, DNA sequence analysis, machine translation that you frequently see on Google, where you want to convert Hindi to English, or in any other language you give in the Hindi and convert it into English. So that is called machine translation task. So given a sequence in one language, it generates a sequence in another language. Named entity recognition. So given a text sequence, you want to find out the entity in the text, which word is an entity, which word is not an entity. And so these are various tasks of examples of sequence model. Since we are more aligned towards the text generation side, one of the tasks which comes under the generative AI is machine translation, because we are generating a text given some previous text. So that machine translation task also comes under the generative AI, unlike others which do not do not come in under the genetic data. So we'll take the example of machine translation task, and then we'll see the whole idea of moving from language models to large language models. However, to give an idea of how RNN works, unlike CNN and LSTM, मैं फास्ट तो नहीं जा रहा हूँ, ठीक है? So, take an example of word level sentiment classification. So, for example, X, this is an input. This movie was absolutely amazing and very emotional. So, what are the words that have the sentiments are labeled as 1 and others are 0. So, you have X and Y. So, some notations just to understand it. You can skip it and you can read it later on also. However, just to give you idea, each word is represented by the X superscript 1, 2, 3, 4 and so on. So X1 is this, X2 is this, and the output Y is Y1, Y2 and so on. So superscript 1, 2, 3 are showing this. And since we have different tasks, Tx, let's say, representing the size of input, and Tx, Y is representing the size of output. In this particular example, your Tx and Ty are of equal size. In other cases, other variants, where let's say machine translation task, where you are giving a sentence in one language, generating sentence in another language, your Tx and Ty will be different. In one language, it might consist of only 5 words. In another language, it might consist of 7 to 8 words to representing the same thing. So this particular example is simplest one, where your Tx and Ty are of same length. And how we represent the words using the vectors, basically. So that I have already explained why you cannot use a standard neural network model to train over the sequence task, because it does not capture the sequence of the input, right? Or also there is another problem which is common compared to all the networks that you study, like CNN or any other advanced deep neural network. In ANN, you have unique weight. So, for example, this is your. Okay, मैंने ज़रा बड़ा एरिया छोटा कर लेते हैं ताकि आपको समझ आ जाए. So, okay. So from each input to unique input to unique hidden layer node, you have a unique weight. So the weight sharing is not there amongst the layers. Whereas CNN, where you use a kernel and you use a kernel that moves towards the image, you have the weights that is shared among the whole input of the image. So if even the size of input, let's say of an image 1024 into 1024 जो आपके मोबाइल में होती है, even for that size of image, you can think of how many weights will be there if you uniquely use those weights. For example, let's say 4 cross 4. So you have image of 4 cross 4. So you have inputs will be 16, and let's say hidden layer nodes are 20. So how many weights will be there? 320. So that even for a small size of input, you have these many weights. So think about 1024 into 1024. How many weights will be there? So weight sharing is not there, which is common problem with ANN. And the major problem is we cannot maintain the sequence. So how a recurrent neural network capture this sequence idea? So unlike a single network, here we have RNN units. What happens? In each RNN unit, we give a word vector, we give a one word, it generates an output, and in between this, we take a context information, again in form of a numerical representation, that you can think of in informal way, that this vector is capturing the context of this word. somehow it is representing this word. So what we are doing, we are feeding this to another RNN unit, which is taking the second word and generating the second output. However, this second output is not only dependent on the first second input, it is also dependent on first output. So this Y2 is dependent on X2 as well as X1, and this Y3 is dependent on X3, and this now this A2 basically capturing the context of both X2 and X1. Now similarly, this A3 is having a representation context from X3, X2 and X1. So towards the end, this last output YT basically not only depends on last input, all the previous input as well. This is how it is capturing the sequence. This is how RNN represented, and these dots basically represent the basic RNN unit having one input layer where you are giving the input, one or two or maybe multiple hidden layers, and the last one is the output layer. Simple, you can think of neural network architecture where you are giving only one word as an input, going from input to hidden, hidden to output layer. And in between this, before calculating the output, the last representation you are taking as an input to another layer. Because first there is no previous word, so we are giving a zero vector, or you can think of a simple randomly initialized vector as a context. I hope you understood. Just a layman idea of how RNN. So unlike other networks, this do it one by one. That's why it is called recurrent neural network. So recurrently you are generating the output. There is a short representation as well. In some of the literature, you will find out this recurrent notation where this represent the context that you are feeding again into the network. So I'll not go into the how it is calculating. So basically, when you have, so let's say you think this as an RNN unit. This is your input where you are giving first word X1. So there are some weights are involved here from input to hidden, represented by WAX. From hidden to output layer, represented by WYA. And then if you're passing to sigmoid layer and then you're calculating the output, so basically those weights are there, WAX, WAY and so on. So from input X1 multiply with the WAX initial weights plus the input that you are taking, other weights are involved, WA plus some bias we added. This is how we do it. We do a weighted multiplication plus adding the bias. If you are not understanding, just you can just skip it, and for the sake of completeness, I'm just explaining. You add the bias and you pass it to the activation function, and then you get the output. And last layer, you take this context linearly transform with some weight, adding the bias and passing to another activation function. You get the last you get the output. So if you don't understand, you just take the information up to this point of time that we give an input to RNN unit, we take the context, we feed it to another RNN unit so that the sequence maintains, and how we are calculating mathematical details I am not going into. So if you even if you want to understand, just ping me out. Okay? Otherwise, because I am going into breadth size, if you want to understand, just let me know. Okay. So I'll skip this part. So in neural network, how we train the model? Using backpropagation. We define a loss function based on the output, and you backpropagate it and you update the weights. Here in a sequence model, we call it backpropagation through time, BPTT, because you can think of this as a timestamp 1, 2, 3, 4 and all. And whatever the predicted output and the actual output will be there, because considering as a classic supervised problem, calculate the loss at each step. You add the loss, it's a combination of all the losses from all the units, the summation of it, and then you backpropagate and you weight the changes of each RNA unit from last to 1. So starting from this RNA unit, you change the weights and update the weights using backpropagation, and then you move backpropagation through time. So that is called backpropagation through time in a simplest terminology. So in forward pass, you calculate the output. In backpropagation, you update the weights of all RNA unit. Okay. So basically, this is the idea. If you have any sequence modeling task where there is only one input and one output, so one-to-one architecture. If you have one-to-many architecture, so you give input to first RNA unit only, and you calculate from all. Okay. What was the example for it? One-to-many.
Image into text.
Again, image have lots of pixels, so that they all are. So in sequence to sequence task, music generation, where we were giving only one input, and we are taking a sequence of output. Or many to one sentiment classification, giving a whole text, and you'll take the output of the last one only, because last output may have the context from all the previous input as well. Now, many to many have two versions, and this is where language modeling comes into the picture. One is like name entity recognition or word level sentiment, where you have input and output of equal length. Language translation is one to many, but you have a different length, unequal length. So then the architecture changes. And yesterday I told you about the encoder-decoder architecture. In case of images, there is same encoder-decoder architecture in case of text as well. So there is one encoder unit which takes the input, do not generate any output. It just generates the context. And towards the end of encoder, you get a vector which consists of context from all the sequence, and that fed it to decoder part, and decoder only generates the output. And that's where generative AI side we are moving, apart from other tasks. This is a more elaborative way. One to many, if you have only one input, what do? You give a initial vector, give the input vector, and you generate output. However, you need multiple output, and this y2 should be dependent on, because there is a sequence. So instead of giving another input, we don't have another input, so we give that output as an input to second RNA, and so on. In case of many to one,
in one to many, is the hidden state of the first unit also being passed to the
yes, that is always there, because we need the context from the input as well. But the output is we are also forwarding, because it is going to maintain a sequence. Here you can see many to many, where you don't have equal length. All the inputs are passed, context is passed, and each time you get a vector, towards the end you get a context vector which captures the whole sentence, and then it is passed to decoder side, which generates the output. And decoder side as well, you don't have the input, so what you do, you pass the output of each unit to another unit. So important. So okay, so I'll skip this part. So because we are going to study the language large language model, so let's pick the particular task called machine translation, where we are generating a data into another form. How RNA unit works? So that, I think yesterday you saw this. Okay, so this is a sequence to sequence model, could be an RNN architecture. Takes a sentence in one language, word by word it takes, and a sequence model generates word by word. A high level representation. Let's go inside it. So inside we have two parts, encoder and decoder. So encoder takes the input one by one in a sequence way, and it generates the context vector. This is important. This context is basically a numerical vector which maintains the context from all the words in the sequence. And that using that context, decoder is generating one word at a time. So okay, so before moving ahead, tell me what could be the problem of this architecture. Anything what you think? Or what is the limitation of this architecture, or what the problem will be there? Even non-technical intuition you have.
With the
Very
ordering.
Ordering this, if I've taken something in the start of the sentence, then remembering that context in the last sentence
So that,
will have lesser weight actually.
So basically, this is one of the problem we have. So bottleneck of the context vector, because the context vector last में ले रहे हैं आप, and if you have a long sequence of words, so maintaining the context from all the words throughout the sequence will be difficult because you have a limited size of context vector. You can think of a board. So this, let's say this is your context vector. If you write only some words, you can understand. If I write all those zero, so if you just fill this board with n number of information and it will mix it up and then nobody can understand. Similarly, it is a context vector of fixed size. If we have more information inside it, our model will not be able to retain the information of the context. Just informal idea. So this was a technical reason. What could be the non-technical reason? So it is taking one by one at a time. Don't you think it is slow? It is not taking whole text at a time and generating the output at a time. It is slow. Taking one word at a time, generating a context vector, then passing it to another unit, then passing it to another. Towards the end, it is generating one. Then decoder is again sequentially it is doing. Though we need the sequence because we have to maintain the order, but it's slow. Now, practical point of view, sir. Let's say you want to build a language model that have learned over all the news available on the internet. So let's say you collected the Google News data, all the data that is available on the Google News website, and you want to build a model that learns over those news and can give you output. Anything you ask from the historical news, it gives you the output. Now you can think of how much data Google News might be having, and if we are giving each sentence or each data to the model one by one word at a time, how much time it will take to learn over it. So that's another reason that the problem it had. So okay, everything is number we have already seen. So how RNN works? So okay, is it running? So initially you have hidden state 0, input vector 1, word 1 input. We process it, we generate one hidden state, context vector to another unit, and we generate one output. Another just illustration in a different. Okay, so final hidden state basically becomes your context vector. So initially first input goes, it generates one context, second input goes, second context, and so on. And last hidden step becomes your context vector, which gives you which fed it into the decoder part. So we cannot train all those initial language models on the whole corpus of the data that is available. So the idea of having pre-trained large language model was not there at that point of time. So also, so you can see here again more detailed. RNA unit is generating one context vector, and then decoder unit is generating one output at a time. So why we moved towards, and why in 2017 need of attention was proposed. Language models cannot compute or large corpus of text, because context vector becomes the bottleneck, one issue, and second, it is slow. Because if you have a large number of sentence which have a large sequence and you want to maintain the context of initial word towards the end, for example, let's say a sentence starts with he, or and towards the end in the same sentence, let's say somewhere him is there, and whether it is her and she. So him depends on whether it is he. If it is her, then it should be she. Somewhere the context from these words in the long sequence must have to be maintained to come up here. But if you have large sequence, then the context vector cannot capture the contextual information in the whole sentence. That's why it becomes a bottleneck, especially for the long sequences. So why? So why not? So idea of so this was the problem with RNN. So to solve it, there are different architectures have been proposed. Before attention and transformer, we had LSTM and GRU. So they use some idea to mitigate this problem. So instead of having a vector which consists of information from whole words, why not just have the context vector from the relevant part of the words? So the words which are relevant to this. Why we are keeping all the words information? So how we are going to select those words which are important, which are not? It is based on the mechanism that LSTM and GRU provided. We are not going to detail. So somehow they LSTM and GRU, you can use some gates like forget gate, input gate to forget information to maintain that problem. So then attention was also proposed to only the whole sequence. Then attention decoder sequence to sequence with attention mechanism has been proposed. And we are generating a single context vector. Now in sequence to sequence with attention, what we are doing? We are taking all the contexts, all the hidden states. So hidden state 1 represent the word 1, hidden state 2 represent the decoder calculates which of the hidden state is important. It does not take the whole, it only focus on the relevant part. So that's where attention mechanism comes into the picture and how it calculates. So let's say 3 hidden states were there, input. How it is calculated, we'll see. Just assume somehow we got those numbers, and those numbers are representing which hidden state is important to understand first. Because the number can be any real number. To make it in between 0 to 1, you use activation functions to squash it. So that's 0.9. Multiply this score to vector, so that give you vector with large numbers, and 0.02 multiplied with h2 and h3 will give you a vector with smaller values. That's why those are actually not shown, and all are added together with all hidden states we have taken. We have calculated the attention, so only one context vector was we got, and this context vector with hidden state gives you the output, first output called I, and then I was given here, and from those hidden vectors, this time second hidden vector score was yesterday सर ने बताया आपको in transformer how you calculate the attention score?
Yeah, QKB.
QK. So one way is one of the ways. So I'll give you more informal idea. So till this point of time, to capture different types of sequence task, and neural network architectures was having problem because they cannot maintain long range dependency and context because due to the context vector bottleneck. So instead of that, we move towards sequence to sequence with attention. Now, whole input at a time and generate the output. And the process that we are doing sequence to sequence instead of sequence to sequence, it should do in parallel, because when we want to make something fast, we need to do the task in parallel so that we can exploit the GPUs that you have in the system, and all the GPUs that you use in infrastructure have to capture this concept of sequence uh, generation, sequence computation into some parallel computation. So that somehow we have to map this concept into matrix form so that those matrix computation can be done in parallel. Right now, why we cannot do this using GPUs and why we cannot compute the in parallel? Because every time the output that is generated is based on the previous input. So there is a that capture the sequence of the input. However, we need not to do in a sequential manner. That's where transformer comes into the picture, where they take the input, whole input at a time, somehow add some embedding that makes it positional aware, what is the position of that word, and converts into alternative representation, which is called Curie key and vector. So and once it can be done in parallel, then you can exploit the GPUs, and then you can train it over large corpus of the data. Or when you can learn over the large corpus of data, the model will be able to learn more about the data, contextual information. From there, all those models like GPT, BERT, T5, Grow model, DeepSeek, जो भी recently announced for the 115, all those models. Yesterday, sir might have told you. So in transformer you have that encoder architecture, decoder architecture. कल बताया था ना सर ने? Okay. So if you have any question from the transformer side, you can ask. I can explain you. जो आपको कल कहीं कोई doubt हो या कुछ समझ में ना आया. Because I am going to skip it. However, if you have any doubt from the transformer side, you can ask. The same examples you might have seen in the previous. Yes.
Superficially tell once again transformers if you have time.
Yeah. Okay. So. Okay.
Just overview once.
Okay.
Very fast overview.
Okay. So the whole architecture is divided into two architectures. Then the word ordering will be lost, and which was the whole idea where we moved from neural network to RNN. Why we moved from neural network to RNN? Because there is a matter of sequencing. So what we do, we add some positional encoding to it, which somehow make this embedding as a positional aware. So now word have their positions. Problem was gone. That the word of the sequence of the word, that order of the word that we have to capture. Now we got it. What we do now, encoder side, we have multiple multi-head attention. So self-attention was a mechanism that I was telling you ki, from the same word, which words are relevant to each other. To calculate it, like we search in let's say YouTube, when we search anything, we give a query, right? And you get lots of videos in it. So each word, the video caption, you can think of it as a key. You match, okay, so which key is important? So this video is important, and you click it, and when you see the content, so that can be think of it as a value. So you give the query, you search it, you match it with the one of the key, and you get the content. The same each word embedding is converted into three parts: query, key, and vector. And each key was used to, each key vector is used to calculating the similarity with the query. So what was the query? See the relevancy. With which word it is relevant to other words in the sentence. This is your query, and you take the key of each word. Done using the vectors. That's why it can be done in parallel. So now one self-attention head might be capturing one type of context. So you need to capture multiple type of context. You can have multiple multi-head attention. Multi-head attention means you have multiple heads. All heads are doing the same thing. Query key vector attentions are repeated number of times. So each encoder layer having two things: multi-head attention to get the context using query key vector concept. Add and norm layer was added because when you compute relevancy, you might forget about the information of the actual input. So you add the input again into the output of it. And adding the input might give you random number. Forward network, again add and norm to do not forget about the information and make it computationally
Normalized.
we do it normalized, and this repeated multiple times to learn the context. In the decoder side, so because we have a lot of data on which we are going to train the transformer. So let's say you have machine translation task and you have gathered data in Hindi language and English language. So you have a pair. English word, English sentence is an input to the output side, decoder side, to make it learn. So here also you have masked multi-head attention. Unlike multi-head attention, there is one concept masked, because we want to only capture the attention between the previous words with the previous word. We don't want to see the attention score, calculate the attention to the encoder last is given to this extra additional multi-head attention, which is encoder decoder attention, to capture the context of the input. Again, it uses alternative way to calculate it, so that computation it can be done faster, and then it pass to the calculated output this words. बहुत मैंने इसको बहुत बहुत रफ और बहुत मतलब हाई लेवल डिस्क्रिप्शन बताया आपको. आउटपुट वाज शिफ्टेड part of the sentence, and the I will be the second sentence, second input. So, any question you can ask. So I can give you the specific answer on the transform. So it was explained there what is positional encoding, what we do, and how encoders works. Usually, when transformer was proposed, in number of encoders was kept at 7 or 8. So if we see the timeline again, we started with statistical pen and paper approach. Calculate the word frequencies, divide the calculate the probabilities, and then see which sentence is most probable to get the output. Then we move towards neural network architecture, because the corpus was increasing. We cannot just calculate mathematically. So neural network was architecture to calculate those probabilities, and then there was so we cannot train over large corpus of data which was available on the internet. So somehow we took a shift. Why not take another alternative approach? Take all those problems and convert it into a matrix representation somehow. That's where attention mechanism and transform came into the picture, and then you can compute it more in parallel, and you can give more data to train. That's where transformers have been proposed, and when transformers came into the picture, then you have all the get the context embedding from the, but you can use it for any classification task or anything. GPT is only decoder side of the transformer, and another variant is encoder decoder T5, which is used encoder decoder. So why we are called? So what is the advantage? You can do the parallelization, handle long range dependency, and performance is superior because you are going to train on large amount of data. So then we move from transformers to large language model. Parameters, then it becomes a large language model basically. You make a complex transformer and you train it over large amount of data, then you call it that language model as a large language model. That's it. So transformers with the ability to process sequence in parallel and capture long range dependency have become the foundation of large language models. So by scaling the number of parameters, scaling on massive data set, transformers evolved as an LLM. amount of corpus. So this is the timeline, how it was started. So once the transformer was proposed in 2017, thereafter all the language models came into it. Because earlier the pre-trained large language model concept was not there. However, once it was the transformer came, because in image it is trivial to understand. Image itself, image is represented as a matrix. So you can perform all those operations in parallel. In case of language, it was not possible. This is just a comparison of GPT-1, GPT-2, GPT-3. So how they evolved. So this was the idea of basically how we have moved from language model to large language model. And then there are other future topics that you can study. How you have moved from large language models to RAG-based systems, retrieval augmented generation, and from RAG models to how you have moved to AI agents. So 2017 Transformer was introduced, then 2021 LLMs came into the picture. 2022, so even LLMs are outdated, right? So even LLMs are outdated. So these days, the more focus on the having LLM that works on a specific task to come up with a compound system, also known as a RAG-based system, and then agentic AI have come into the picture in 2024. Okay. So there are lots of other things were there, but I think for the introduction part, I think this is sufficient. So this is, and towards the second half, we'll have a demonstration of for both coders and non-coders how to use the LLM.